Welcome to the class Advanced Calculus and Complex Analysis. Today we are going to learn one of the most important theorem, Gauss divergence theorem. This is the statement of Gauss divergence theorem. Basically, V is the volume bounded by the closed surface S, and F is a vector point function which has continuous derivatives in the volume V. So then this left hand surface integration will be equal to the right hand volume integration. So basically in this statement it is saying you can do this surface integration in the left hand side. It is basically from the surface integration LHS to the volume integration RHS. So surface, it is saying you can do the surface integration in terms of the volume integration, and as it is n is the outward normal unit vector at any point on the surface S. So this is the first question, which is on Gauss divergence theorem. So use Gauss divergence theorem. So we'll do this surface integration in terms of the volume integration over the surface S of a cube bounded by the coordinate planes and the plane x is equal to y is equal to z is equal to each term actually a x y x a y a and z a. So it is given in terms of the surface integration, but we will convert it to the volume integration and accordingly we will evaluate it. What will be the solution of this one? By using Gauss divergence theorem. Okay, so what is the statement of Gauss divergence theorem basically? So statement, it is saying, just now we have seen, so LHS is the surface integration, it is a vector, and n ds is equal to the volume integration V and divergence F dV. Okay, so this is the statement. So LHS it is given. We are going to find out this RHS volume integration value. So now, so what is the LHS one? That one let us see. Then accordingly we will see it here, because we have to find out the what is F. Okay, so now what is this implies? So LHS is, what is that? F into NDS. Okay, so now F into NDS, that things we'll see, and that F into NDS you can write in terms of, in this form. It is basically F1 dy dz plus F2 dz dx plus F3 dy dx. Okay, so this is the F into NDS, this one, and RHS, that is volume integration V, and divergence of F, that means it is dou F1 upon dou x plus dou F2 dou y plus dou F3 dou z. Okay, this one, and it is dv means dx dy dz. Clear? So what is F basically? Where F basically, F is equal to, so it is the component of F1 I plus F2 j plus F3, this is actually F3 F3k. Okay, and so now by using this one, now we are going to evaluate it. So then if you compare with the what is F is, it is given. So if you compare this question with the previous relation, then what we are getting? So therefore we are getting F1 is equal to x cube minus yz, okay, and F2 is equal to minus 2x square y. And what is f3? F3 is, we are getting, it is z. Okay, so now you can do the partial derivatives because it is needed to evaluate the volume integration. 2f1 2x, 2f1 dx, what you are getting, it is 3x square. Simply do the partial derivatives. 2f2 dou y, it is equal to minus 2x square. Okay, and dou f3 with respect to z, so that is equal to 1. We are getting it. So now what is the right hand side? Therefore that the right hand side volume integration, so that volume integration v, and that is 3x square minus 2x square plus 1. We are getting it. And that what is dx, dy and dz. Just we have substituted that above values in that volume integration form. Okay. So now what are the limits for x, y, z? It is given straightforward because it is the cubical form. So that means x is starting from 0 to a, and y also starting from 0 to b, z 0 to c. These are the limits. Okay. So and what we are getting, it is basically x square plus 1 dx, dy and dz. Okay, as we know the basics of triple integration, we'll do with respect to x first, and we'll substitute the limit for x, and next with respect to y, and we'll substitute the limit for y, and next we will substitute, we'll do the integration with respect to z last, and we'll substitute the limit for z. Then what we'll get? We'll get a cube 1 plus a square by 3. Okay, so this is the value of that integration by using the Gauss divergence theorem. So basically it was actually surface integration. We have converted to the volume integration, and we are getting that integration value a cube whole into 1 plus a square by 3. So now just like the Green's theorem and Stokes theorem, if you want to verify, so what will be the LHS value and RHS value, both are coming same or not. So for that one, let us see this problem. Verify Gauss divergence theorem. It is the different. Applying means only will do that RHS integration things for the theorems, but verify means we have to evaluate LHS value and as well as the RHS value, and we'll compare both the values are coming same. So similarly here Gauss divergence theorem for this F taken over the rectangular parallelepiped. So here A, B, C are constants, and these are positive constants. X is varying, x-axis is varying from 0 to A, y is varying from 0 to B, and z is varying from 0 to C. That means if you draw the graph in the 3D plane, so that means you will get one rectangular parallelepiped. So suppose A, B, C are different. So if A, B, C, if you consider both are same, means all these threes are same, that means we will get one cubical form. So now let us verify this Gauss divergence theorem for this problem. So what is the statement? Statement of Gauss divergence theorem we know. So it is the surface integration LHS, that is NDS, which is equal to the volume integrations right hand side, it is divergence of A dV. Okay, so one by one we can see, and what is given F. So here F is given, so where what is F? F basically it is given, we know F is equal to F1 I plus F2j plus, so that is F3k. Okay, so this is actually F3k. So if you compare this F expression with the expression given in the question, then what we are getting? Therefore we are getting F1 is equal to x square minus yz. Okay. So and F2 we are getting, F2 is equal to y square minus zx. It is given in the question. Just we are comparing it. So and what is F3? F3 we are getting z square minus x of y. Okay, xy. So actually in the RHS, in the volume integration, divergence f also you have to calculate. Let us calculate divergence of f as we are getting f1, f2, f3 here clearly. Okay. Now we are going to find out the divergence of f. Divergence of f. Okay. So this one we know. So that is dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. Okay, this one already we have f1, f2, f3. So you substitute it, then automatically you will get it is x plus y plus z. So these things we have obtained. So easily we can do the integrations, so that LHS and RHS. So let us find out RHS values, because that volume integration just now we have discussed in the previous question. So let us that find out the volume integrations value. So that is, we know it is divergence of f and dv. Okay, so that divergence of f you substitute and substitute the limits of x y z. So you will get, suppose x limits x is equal to 0 to a, y limits from 0 to b. What about z limit? Z limit is 0 to c. Okay, 0 to c. And what is divergence of f? It is 2 into x plus y plus z. Okay, x plus y plus z. So and it is dx, dy and dz. Okay, dx, dy, dz. Fine. Dx, dy, dz. So what will be the value of this one? So this value is, if you do the integration, just simple integrations of all triple integration, you will get f abc into a plus b plus c. Okay, this is the RHS value. You keep in mind this RHS value. Now we are going to evaluate the LHS value, and we'll see the LHS and RHS value, both the values are same. That one we are going to do it. Okay, so now we are going to find out the LHS value. LHS value is the surface integration. What is that form? LHS. So that is equal to, we know that is double integration over the surface S and f n ds. Okay, and f dot n ds. So now to evaluate this one, actually you have to draw the graph. What it is saying, that the graph, let us see. So that means it is one parallelepiped. Suppose it is x axis, it is y axis, and it is z axis. So let us draw a graph which is the form of parallelepiped. Okay, and we can give the name, it is O and it is J. I am giving the name just like this, and you can give the name different way. G, and this is my point O, F, and it is E. Okay, so there are how many surfaces? There are six surfaces there. Okay, six surfaces. So for this one, that means in, but over the surface S, what is S? S is the combination of these six surfaces. So that means this one, this surface integration, basically the over the six surfaces. What are that surfaces? So one surface is, look at the graph and you can see it is OABC. One surface is OABC. Okay, so that means OABC F dot NDS, F dot NDS. So similarly the other surfaces, so other surfaces BCDE, this is another surface. Similarly F dot NDS, you fill it, and so six surfaces, note it down. So OA, FG, and here you write it that same thing, and OC DG, OCDG, okay, OCDG, so this one plus OCDG plus AB, EF, okay, plus, that means 6 surfaces you have to write. So EF, EFGT, EFGT, and this one F dot N dot DS, okay. That means these 6 surface integrations you have to do. Suppose it is my equation number 1, look at the graph and accordingly do. So suppose on OABC, what is the value you substitute, and on BCDE, what is the value substitute, then 6 values you substitute, we'll see is it matching with the RHS value or not. So first let us consider OABC. So try to understand for one surface, for then the remaining surface you can do easily. First we will look on that OABC surface, how I am doing. OABC. OABC means it is on the XY plane. On the XY plane means what about Z axis? Z axis is 0. OABC, that means XY plane, Z is 0. But what about N? N means it is the outward normal unit vector. That means it will come on the in the negative side. Okay, that means it will be minus k. And what is ds? It is dx dy. These things we can identify, and already you have seen in the Stokes theorem. So let us see what is the value of this surface integration on OABC. So on OABC. Okay, on OABC we will see what is that surface integration value. So on OABC, what we are getting, thus we have to note it down. What is n? Just now I told you n will come, it is minus k. Okay, so now what is ds? Ds you will get, what is ds? Ds you will get, it is dx dy. Fine. So this one, so what about z? Z is equal to 0. As z is equal to 0, that means dz automatically will be equal to 0. Fine. So what about then f dot, this one you can calculate it here. So then what about f dot n? Okay, what is f dot n? F already in your hand, and n you do, n means it is actually minus k, then it will be the dot product. Okay, so then you will get minus z square. Do this dot product, you will get minus z square x. Fine. So then what is that integration value on OABC surface, that f n ds, that is actually will come. So that means basically it is the double integration. Okay, we are getting the double integration, and it is xy, okay, xy and dx dy. Fine, dx dy, that means it is the limit for, suppose x is equal to, because we are doing with respect to x first, that means x limit will come, x is equal to 0 to a, and what about y? Y is equal to 0 to b. Okay, this is the things. Now you can do the integration with respect to x first and substitute the limit for x, and next with respect to y. So then we will get what is the value. It is clearly showing it is a square b square divided by 4. This is the first surface integration value on OABC. Clear? So similarly, one by one you have to do. That means that the 6 surfaces you have to find out what are the values. So let us find out for on EF, EFGD. Okay, for EFGD. That means for the other side, that above sides. So that means n is equal to k. Okay, n is equal to k. What is z? Z is c. As z is c, so that means automatically dz will be equal to 0, because if you do the derivatives, dz is equal to 0. Fine. So then what is that integration value? In this case directly I am writing. So basically it is x is 0 to a, x is 0 to a, and y is equal to 0 to b, y is equal to 0 to b, and substitute z is c. So that means it is c square minus xy, so it is dx dy. Okay, so that means you will get here abc square minus a square b square by 4. So two values we are getting. So another four values are there. So if you understand one surface integrations, that remaining automatically will get. So similarly on OCDG, OCDG, what will be the value? On OCDG, I am writing in short form, OCDG n will be equal to minus I. Okay, n is minus I, x is equal to 0. Then what is dx? Dx will be equal to 0. And what is the integration value? OCDG, just like the previous OS. So you will get b square minus b square c square divided by 4. Okay. So now O on ABEF. Okay. On ABEF. So ABEF, what is n? N is equal to I. N is I. What about x is equal to A? So that means dx is equal to 0. Okay, so in this case on ABEF you will get the answer is a square BC minus b square c square divided by 4. Okay, 4 parts over. Similarly on OA, on OAFG, on OFG, on OFG. So on OAFG, what is n? Because if you identify these things, then remaining things is easy for you. Okay, region. So what is y? On this surface, y is equal to 0. So then what is dy? Dy will be equal to 0. Is it clear? So then in this case, what is the surface integration value? A square c square by 4. So what about on the last one? So it is BCDE. Okay, BCD. On BCD. On BCD, your n is equal to j. N is j. So what about y? Y is equal to b. So that means it is dy is equal to 0. Fine. So in this case, your answer is for the surface integration on BCD, it is AB square C minus A square C square by 4. Okay. So 6 values you are getting. Now substitute in that LHS form. So that means what is LHS? What is LHS? That means that is 6 things you substitute automatically. We'll see what is the result. So A square b square by 4, all 6 values you substitute. So a b c square minus a square b square by 4. Okay, already you have these values, and b square c square by 4 plus a square bc, so minus b square c square by 4, fine. So plus a square c square by 4 plus a b square c minus a square c square by 4. Something will cancel and you adjust it, it will come simplify. So it will come abc plus a plus b plus c. Okay, and we have seen this is actually the RHS. So what we are getting LHS, and which is equal to RHS for this question by using Gauss divergence theorem. Okay, so that means Gauss divergence theorem is verified for this problem. Thank you all.